Alright, good morning ladies and gentlemen. As you can see, it's Monday, May 18th, and this is really the last week of videos for the normal school year. So I thought I would treat this a little bit differently and go over a few mathematical subjects that I find either fascinating or very important to our education. And today I was going to continue talking about probability as we were last week, and what we call the Monty Hall problem. It's a very famous problem about probability, and it's translated into our society through many things, such as let's make a deal. And just in case you've seen that television show with Wayne Brady. Imagine you're on a game show. There are 3 doors. Behind 2 of the doors are goats, and behind 1 door is a new car. Ladies and gentlemen, you want the car, you do not want the goats. That's an assumption. You get to pick a door. Then the announcer reveals a door that has a goat behind it. Then you are given the option to switch to the other door or stay with the one that you have. So once again, 3 doors. Door 1, 2, and 3. You pick a random door. And when you pick that random door, one of the goats is revealed. That doesn't mean that door is taken away. That just means, hey, there's a goat behind this. Now you're given the option, hey, do you want to switch to the other unrevealed door, or do you want to stay with the door that you have? And so the question really boils down to, do you stay with your door, or do you switch with a new one? Now you might say, oh, this is 50-50, there's 2 doors left. It doesn't matter whether you stay with this door, or you go with a new door. You have equal odds of getting that car. Now, ladies and gentlemen, I want you to know that that is not true. There is a mathematical solution to this problem because all probabilities are written mathematically. So therefore, if you know the math behind something, you do have the edge on the probability. Now, in order to do this, let's see if this is going. Oh, computer's having a little bit of an issue right now. We have to assume a few things. 1. If you're picking randomly, you have a 1/3 chance of getting it right initially, because if there's 3 doors and it's behind one of them, you have a 1/3 chance of getting it right. That's because of the rule of complements, we have a 2/3 chance of getting it wrong. And remember, if you add the 1/3 and the 2/3, you get a probability of 1 at the end, which is the 100%. So there's nothing that's left out here. Everything makes sense. So you have a 1/3 chance of getting it right, you have a 2/3 chance of getting it wrong on your initial pick. Because the car can be anywhere, and a goat will always be revealed, it doesn't matter what door you choose. It does not matter what door you choose. You can choose door 1, you can choose door 2, you can choose door 3. It does not matter what door you choose. And so for the sake of this argument, we're going to say we always choose door number 1. We're going to assume that we always pick door number 1, not door number 11, door number 1. And obviously, basic rules of probability apply. You can't have a probability greater than 1, you can't have a probability less than 0. If it's an event, it has some sort of probability, so on and so forth. So the question applies, it still applies. Do you pick the door, do you pick the other door, the revealed door, or do you stick with the door that you have? Assume these are 3 doors that do not have a good foundation since they're crooked. Like, let's say this is revealed, and this is the door you picked. Do you go with this, or do you switch to go with this one? So, let's look at the solution. Now, I'm going to draw really about 2 different diagrams in order for us to understand the solution. First one is I'm going to try to be the clearest in describing that, because a lot of people overthink the solution or underthink the solution. Barely anyone spends the right time thinking about the solution, and that a lot of people say, oh, well, it doesn't matter because it's 50-50, so I'm going to stay with what I have. Well, that's definitely wrong. The correct answer is you should always switch. It's more mathematically beneficial for you if you switch doors. Now let's consider this. As we said in our assumptions, it doesn't matter what door you choose. So for context's sake, we're going to assume that we choose the first door. This is going to be my door number 1, my door number 2, and my door number 3. There are only 3 options of where the car can be. The car is either, for first option, it's car, goat, goat. For option number 2, it's goat, car, goat. And for option number 3, it is goat, goat, car. Now, for this, and for this situation, we're going to consider a couple things. We're going to consider whether you stay or whether you switch. And we're just going to go on a win-loss thing. If this was your choice, and let's label our axes, your choice. And let's say you chose 1, or no, actually, that should be your choice. You chose number 1, and we don't know it yet, but that's the one with the car, and the other ones are goats. If you stayed with this one, you won, and if you switch, you lost. Oh, hello, Minerva. I got a kitty up on the bench with me. But let's assume the other ones that when you pick this one, that this is the goat they're going to show. And when you pick this one, this is the goat they're going to show. Pick this one, and let's just assume that this is the goat they're going to show. Well, if you pick this one, and that's the goat they're going to show, when you switch, you win. If you stayed, you would have lost. And if we consider the third option, if this was the car, this was the door you picked, and that was the goat they showed, well then switching would obviously give you the win. So staying would have lost, switching would have won. So out of this, just consider just these portions mathematically. If you stay, you lose, or if you stay, you win roughly 1/3 of the time. If you switch, you win 2/3 of the time. Now these are the only possibilities that you have. Like, you have to have a car, you have to have 2 goats, and because of how they're distributed, you can only have 3 different ways. So when you consider it, you win 2/3 of the time if you switch. If you stay, you win only roughly 1/3 of the time. So the one that has the higher percentage of winning, or the higher chance of winning, is the switch one. Now, another way I would have explained this is that consider you do have the 3 doors. And once again, for argument's sake, we assume that we choose this one. Well, if that is, as we discussed previously, if that's a 1/3 chance of winning, what's the probability of the chance of losing? 2/3, obviously. Which gives you 100%, because that's just basic probability. Now, opening the door and revealing a goat behind it does not change this statement. If this goat is revealed, it does not change this statement. You have a 1/3 chance that you picked the right door initially and a 2/3 chance that you picked the wrong door initially. That statement does not change. It would only change if it somehow the third door, that second door is eliminated and you only have 2 doors at all. But because there's 3 doors, the probability of 1/3 and 2/3 still stand. And so, if you stay, you're stuck like this. If you stay, you're stuck with this being your winning move, 1/3. But now, if you switch, this probability is reversed. Like, okay, well, if I only had a chance to win on my first pick of 1/3, and I had a chance of losing being 2/3, well, if I switch, you switch the probabilities. Winning now has a chance. Oh, I didn't need to stay there. I meant to right switch. Winning gives you a probability of 2/3, while and your probability of loss is only 1/3. Gives you once again a chance of 100%. So, I actually had a lot of fun working on this one over time because I love games, and it's entirely a game, but we have to consider a few things. Let's say the final word, switching, is more mathematically relevant, and it's more mathematically beneficial. Does the solution always work? No. I don't want any of my students getting onto a game show, getting into the situation, and then switching, and it not working out for them, and saying, "Oh, I blame my teacher." Don't do that. So does the solution always work? No. Because a probability is never fully guaranteed. If a probability is fully guaranteed, it's not a probability anymore, that's an assurance. And so, the solution doesn't always work because probability is never fully guaranteed. But we know that probability follows specific mathematical equations and sequences. So knowing the math and knowing how it works is better for you. It gives you a better chance of success. And with that, ladies and gentlemen, I'm going to sign off for now, and I will see you tomorrow. Hope you have yourselves a good